Okay, so we're officially starting, and I'm not sure who all is there, but you can chime in either on Slack or by talking to me. We've got any number of things running, and spring break week has been a very busy time for me. I don't know about for you guys. I've been at home all the time, but I found it to be a very hyperactive experience because I feel like I've been kind of acting like a babysitter for people that don't know what to do with their time. And I'm not picking on anybody. It's just that most of the graduate students I have are working from home. So um, people are getting their work done and they're actually turning things in early, which is never usually happens during spring break week. So right now, um, I've already put up, and I didn't refresh this web page, but earlier this afternoon, I already put up set number 8 and set number 8 with hints, and that's the first problem assignment out of chapter 4. So that's where we're going to be spending the entire time lecturing today. I will jump over and take questions on the assignment, but I'm going to do that a little bit later. I've got my solution sitting here on my other computer screen, so I can take questions on those two problems. We will be able to look at the assignment sheets too. Let me just move those into my folder since I didn't get that done yet. So I'm just moving these hints pages in there. We will want to have this to get access to the chapter 4 Jupyter notebook that we'll be looking at momentarily. So now I'm going to quickly go back and take a look at angle modulation where we left it from last 2 weeks ago. And I'm actually going to go do an experiment here because yesterday my stylus would not function at all. It was very disappointing, and it turns out I made the right move last night, and that is I just used my mouse to draw on the screen, which wasn't very good, but my system needed to be totally rebooted for it to come back to life again. So hopefully it stays working today. So getting back to where we had reviewed through on that last lecture before the break started, we were looking at the introduction to angle modulation. I'm just going to quickly get us back to where we left off. Angle modulation puts all the information into the argument of the carrier, so everything is housed right up in this area. And some fundamental definitions that we have is what is the instantaneous phase of the carrier? Well, that is the entire argument. So that is all of this, omega ct plus phi of t. But the deviation, which is where we're going to be sending our information, that's housed in just the phi of t. So then we have the phase deviation is phi of t, and then the secondary interpretation of what's going on with the argument is the instantaneous frequency and frequency deviation. So that's taking the derivative of the argument of the cosine with respect to time, and then it breaks out into the constant, which is the carrier, and the phase. And frequently what I like to do is I like to put a 2 pi in here, so this will be the instantaneous frequency deviation in hertz. And then that means you're just going to be dividing by 2 pi everywhere. So you'll have frequency in hertz. And if we were doing the lab with a spectrum analyzer, that's the type of thing that you would be doing in lab number 5. That's a great disappointment to me, but we've worked things through on the lab, and as I left it today with Daniel, I really want all of you in the lab to read through the first part of lab number 5. It introduces you to the instruments, what they can do, and then reflects upon the measurements you can make, and then of course things in Jupyter Lab. More discussion will be coming tomorrow when you get the assignment as to what you're going to be doing in the lab with lab number 5. And I won't take that up right now. If you want to hang out at the end and ask me some questions, we can do that. But at any rate, moving along, there's two basic types. Now that we have instantaneous frequency, frequency deviation, instantaneous phase, and phase deviation, there's two basic types of angle modulation. There's phase modulation, where you make the phase deviation be proportional to the message, and that's this form right here. Kp is that deviation constant, and Kp just simply converts the units of m of t into the units of radians. The second type is frequency modulation, where you make the frequency deviation be proportional to the message. So you have a constant Kf, which converts the units of m of t into radians per second. So just a little comment here. The units that you come out of that would be radians per second, and then divided by units of m of t. Oftentimes it will be volts if it's a voltage controlled oscillator, and we'll get into that in a little bit here too. That's actually where the lab experiment would have started. But what we end up doing very, very frequently, extremely frequently, is we end up working with Kf not as radians per second per unit of m of t, but instead define f sub d as the deviation constant in hertz per unit of m of t. That's the more common terminology that I like to work with. So this was a quick example of phase modulation, where we're just modulating the carrier with a step. So this, in this case, m of t is this step. We're just going to jump the phase at t is equal to 0 seconds by pi over 3 radians. And if we wanted to then look at what the FM signal, how we would form an FM signal, we have to go in and put in the instantaneous frequency, but we have to integrate that to get it to phase. So this is going to become our phi of t. That's the phase deviation. So we integrate the frequency instantaneous or the frequency deviation to get it to phase, and then we've got the units on there that are appropriate for our configuration. I'm using FD, and the radians are actually coming through from right in here. That's where the radians part comes from, because FD has units of hertz per volt, and then we're integrating volts, and we're getting volts again, and we're converting that then to radians. So here's an example of the pi over 3 phase step at t is equal to 0, and then a 3 hertz frequency step at t is equal to 0. And there's a couple, I think there's a couple of homework problems that you'll be doing on this set number 8 that deal with that type of fundamentals in both frequency and phase modulation. So you get used to the idea of doing derivatives and integrals of whether it be a frequency or phase deviation. And you know that I've been teaching the phase lock loop synchronization class this semester, so in that class we've been spending a lot of time with phase and frequency deviations on carriers, because that's what the phase lock loop tracks, and we'll be getting into phase lock loops at a more fundamental level later in this chapter as well. So now we're going to sort of sidestep the main theme of angle modulation and consider a special case of angle modulation called narrowband angle modulation. And those of you taking the lab have been exposed to this already, because the narrowband receiver that you worked with in lab number 4 is designed, it's a dual conversion receiver, dual conversion superheterodyne. It's designed for processing narrowband FM signals. In the case of the lab experiment, you were listening to the weather channel at 162 Now my brain's drawing a blank. 162.475.
475.
475. I used to have that memorized, but my brain is cluttered with too many thoughts. But that's a narrowband FM signal. So now let's just kind of understand what that looks like. You're going to be intrigued by the fact that it's very similar to amplitude modulation. So here we take and write the angle modulated signal as the real part of a complex exponential, and breaking that complex exponential up into the product of the two terms, the carrier term and the phase deviation, and then expanding the e to the j phi term in a power series, something you studied back in calculus. Do a power series expansion of just the phase deviation component, and we see we have the first two terms are what we're mostly interested in. So the narrowband approximation is going to say that magnitude of phi of t is much less than 1, and then this will be the focus then for narrowband angle modulation on just the constant plus the linear term j phi of t. So when you put that inside of the real part operator, we bring in the carrier term, and then we've got what appears to be almost like an amplitude modulation, except that we don't have a cosine carrier times its constant and then a cosine carrier times the modulation. Instead, we have a quadrature relationship. We have the pure carrier is cosine and the quadrature part is the sine, and that's where the message resides. That's where the phi of t part resides. So you can draw a block diagram of that system that follows immediately from this math expression right here, and the block diagram looks like this, and this just happens to be the way it's drawn in the book using a sine. So you've got the sine carrier amplitude that gets multiplied times the phase deviation you want, phi, and then that minus sign is sitting right in here, and that's this minus sign. And then you add 90 degrees onto the sine, and that transforms it to a cosine. So that ends up synthesizing this term in the block diagram. So what's interesting about this is it looks like amplitude modulation, but it's not really amplitude modulation. It is truly angle modulation. And under this model in here, if we go all the way back up to this form, or actually go all the way back up to where I started from, right in here, it might be that. My finger went awry on the touch screen and it went off and did what I didn't want it to do. Expanded everything out really big. I'm standing up right now at my kitchen counter, which is a little bit too low, so I'm kind of making myself a little bit awkward, but I can't stand sitting the whole time either. So what I wanted to do was, well, I guess I wanted to use this down here. A characteristic of angle modulated signals is that they're said to be constant envelope. And that's because this is a constant. So even though that signal has the appearance similar to an AM signal, it is not constant envelope. AM signals are definitely not constant envelope because the message ends up being, in an AM signal, you can derive from the envelope itself. In an angle modulated signal, not so. And that comes into being from down in here, the fact that we have sine and cosine. So we don't have an envelope that is time varying. It's a constant envelope. So here's an example of just carrying it through with narrowband tone modulation where the message is a cosine. You can take the FM version of the angle modulation. So the message is AM cosine omega MT. We have to integrate that to get the phase deviation, and that becomes a sine, and then there's some scale factors that get thrown on there. So we end up with this AM FD over FM is the scale factor that we have, and it ends up being called a modulation index shortly, but right now we haven't named it that yet. It will be known as the modulation index in angle modulation with a sinusoid. So if you break that down and break it down using the approximation that we've been using, namely the power series expansion. So that's why the approximation is in there. So we're just keeping the first two terms of the power series, and then we end up having a carrier term and upper and lower sidebands. But the upper and lower sidebands are on a sine carrier, and they're of opposite signs. So we have another peculiarity in this narrow band. We have a plus sign at the frequency below the carrier, and then we have a minus sign at the frequency above the carrier. And if you draw out a picture of that, which is what the book does, which is not really a proper amplitude spectrum because I'm showing sine on there, it's just trying to emphasize the fact that the carrier is on the cosine, and then the sidebands are equal and opposite in sine, but they're in quadrature. So that's cosine, and that's sine. But it does kind of have that appearance. So we're going to depart from that, and we're going to then extend on to the more general case of the spectrum of an angle modulated signal. In this case, we're going to assume sinusoid angle modulation. So that's all we're going to do here. And one of the things about angle modulation, it's said to be a nonlinear modulation. So getting the spectrum, the true spectrum for an arbitrary type of message is actually no small job. It's actually very challenging, and very often you end up doing things in simulation to get there using power spectral density estimation techniques, things that we've been doing in Python for quite some time. We use that function called PSD, power spectral density estimator, on a long array of data. So we're going to handle the single sinusoid case right now. So we're going to let phi equal beta sine of t, and like I was saying before, beta is called the modulation index. That's what's the peak phase deviation. So this controls the peak phase deviation. That you're imparting to the carrier. And if you were to take the derivative of that, you would get the peak frequency deviation, and we'll be seeing that in a bit here too. So our transmitted signal is of this form when we replace phi by beta sine omega m, and then we can do the same setup with complex sinusoids and taking the real part, and then we become curious about what is the spectrum of that. That's going to be a periodic signal. It's beta sine omega mt. Beta is a constant, but sine omega mt is periodic, and its period is 2 pi over omega m. So because it is periodic, we can just blindly say it will have a Fourier series expansion, because all periodic signals have a Fourier series expansion. So we go ahead and say it has an expansion, and the harmonics are multiples of omega m in radians per second, and then we just need to find the coefficients. And we can do that using the Fourier integral. And that's written out at the top here. And then it's simplified. Well, I guess it's not simplified. I just group it into two complex sinusoids and then group it together. All I was doing is rearranging things, having the negative exponent. So we have a negative exponent. Then finally, here, there's a change of variables that's done. This is all kind of like when you start at the top of the page here, you say, I don't like the looks of that integral no matter what you do to it. If you transform it, do change of variables, change limits, it still doesn't look very doable. It doesn't look like anything you're familiar with, and you're right. If you would take an advanced differential equations class, you possibly would run into a differential equation that would have this solution. Did anybody ever bump into Bessel functions in their differential equations class? Just curious. Okay, I took advanced differential equations, and that's where I first bumped into it. Then in fields and waves, you bump into it, and in physics classes, you bump into it too. So the blue box there is into a form that either is the complex exponential form or a cosine form. And if you go to a handbook of integrals or you look online for what is the integral, that's a definite integral, since you're integrating from 0 to pi, it becomes this special function in mathematics, and this is the J sub n Bessel function. So it's got a name. The name is named after the founder of the function when he was solving a particular differential equation, which now has his name. So Bessel is the guy's name, and this is the first kind of order n with argument beta. So if you've never dealt with special functions before, here you go. This is a whole family of special functions. The first kind of order n with real argument beta. And MATLAB has these available, Mathematica has them available, and Python has them available, and we'll see how we access these particular special functions. Since some of you in the class now are taking problem stats, you've run into at least one special function by now, and that would be the error function, the ERF, and then the complementary error function. Is that true or not true? And if you don't want to answer me, at least somebody wants to say, yeah, I did do it. You can answer me in Slack. Is it the ERF or the ERFC that you've seen already, or both? My guess is if you've seen one, you've seen the other. And that is the special function that you get when you either integrate you integrate from 0 to a point of the bell curve, the Gaussian PDF, or you integrate the tail of the Gaussian PDF, you get the complementary error function. So that's another special function, and special functions are just things that aren't solvable in closed form. You have to have some sort of a series representation, but they've been abstracted to carry the name of the person that invented or first bumped into them, in the case of the Bessel function at least. So Bessel functions have different properties. One property is called a recurrence relationship, and this is what I'd call a bootstrapping formula. So if you have representations for, say, J0 and J1, then you can carry that up to get J2 for any argument. And once you have J2, then you can take J1 and J2 and you can generate J3. So you can step up using the recurrence relationship. And that's what this equation is here. if you are looking at even orders, so it can be j of 1 or j of minus 1, that's the function is even if n is even. So j of minus n of beta is the same as j n of beta, and if n is odd, then there's a minus sign in there. The functions plot out looking like this as index beta changes, and the zeros of the Bessel functions, which are points here where they cross through 0, those end up being important in spectral analysis. And we'll see how that works out. And I'm just going to flip back here. If my system will let me have this luxury, we'll see once. I'm going to go down here and look at the formula sheet for a second that you've had for a long time. There is on the last page Bessel functions. So these are Bessel functions, and the single underline and the double underline is something that we'll talk about here eventually. Here's a plot of the Bessel functions, and then here's a plot, or here's a table showing the zeros, like J0 of beta goes through 0 when beta n is 2.4048, 5.201. So if I jump back over here, this point right here is a 2.048, and this is the 5 point. Let's see, now I have to follow J0, which is this curve. It crosses 0 right in there at that point, and that's the 5 point, whatever I said, 5.5201. So those are curiosity things, and if you were doing the lab experiment with the equipment in the lab, it was something that you got to investigate live. If you had an analog discovery, you could demonstrate it live too, because you can frequency modulate the signal generator in the analog discovery. But we can generate FM modulation in Python as well. So there's the plot. Here's a table of the zeros. So now we've kind of looked at the backside of what the Bessel functions do in terms of getting the spectrum. What we've done now is we've replaced this e to the j beta sine omega m, that's our sinusoidal angle modulation. We've replaced that by this double-sided sum of basis functions e to the j n omega m, as used in any Fourier series representation, and the Fourier coefficients are the j n of beta. And then if we go ahead and combine the exponentials together and take the real part, we get the cosine. So now we're going to get a sum of spectral lines, and this is kind of indicative of the single-sided line spectrum, where you just focus on what are the spectral lines on the positive frequency side, and you don't think about splitting everything in half like you would if you're doing a two-sided spectrum. So here, as n runs from minus to plus infinity, it's giving you spectral lines that continue to expand outward from either side of the carrier frequency Fc. So this is what the spectrum looks like. And just to pause here for a second, if we were back on double sideband and we were modulating the carrier with just a message at frequency FM, that would be this inner rectangle. This would be, the bandwidth there is 2 times FM. So I want you to kind of get a grip on the fact that with angle modulation, the bandwidth is expanded beyond the 2 times FM that we would have seen in double sideband. We're putting in just a single tone, but as we drive the modulation index beta harder and harder, the Bessel functions produce more and more components, and it spreads the spectrum out considerably. if we were looking at this as being phase modulated carrier with a sinusoid, beta is Kp times A, whereas if we were looking at it as frequency modulation, then the modulation is, in the phase domain, it's Fd over Fm times A, so beta is a combination of the deviation constant for the FM modulator, the modulation frequency, and A. So those three together form beta. So this picture shows the progression of beta getting bigger and bigger. When beta is very small, that produces the narrowband FM case, narrowband PM FM. And a characteristic of the narrowband angle modulation case is only one sideband pair. But although I'm writing that on the slide, only one pair, in actuality there are pairs outside of plus and minus FM about the carrier, but they're just way down in decibels. This is the linear axis spectrum, so it looks like there's nothing there, but actually there is something there because the Bessel functions start becoming active as soon as beta is greater than 0. And that we'd be able to see from this picture over here. If we start zooming in into this area, we're going to see all the Bessel functions immediately start becoming active as soon as beta is greater than 0. J0, which is the carrier term, is 1. It starts getting smaller, and then the amplitude values of the other Bessel functions start to grow as beta gets bigger. So as beta gets bigger, we're seeing more and more sidebands appear. So as soon as we start seeing significant levels for sidebands greater than one pair either side of the carrier, then we're no longer in narrowband. And we can see if we increase beta to the point where the J0 Bessel function hits its first 0, then there's no spectral line in the carrier. As beta continues to get bigger, the first pair of sidebands now pass through J1 equaling 0, and so on and so forth. It just keeps sort of growing and growing and growing. And if I was to jump over to the Jupyter Notebook right now, this is designed to do everything for the rest of this chapter, so I've got the synchronization module is included because that holds some phase lock loop models that we'll be using later. But in order to play with the Bessel functions, I need to import from the SciPy library the module called Special. And once I get Special, I get access to all kinds of special functions, and I just will show you that here by hitting dot and tab. It should be coming up with a long list, and this list is huge, but Bessel is in here for sure, up in the B's. And then I'm mentioning the error function, right? So if you look under E, we'll find the ERF, the ERFC, the error function inverse, and some other things. So the special function library of SciPy has got a lot of these special functions categorized. So the J's are the Bessel functions that we want, the JN Bessel functions. So I'm using special.jn, and if I go inside the parentheses there and then hit tab, it'll tell me what it is. It says at the very bottom here, Bessel function of the first kind of real order, possibly complex argument. We're not going to use it that way. So the first argument is the order, and then the argument, which we're calling beta, is the second argument into Jn. So what I did here was I just set up a loop that loops from 1 to 5, and then I set up a range of values for what was beta, here I call it xj, to continue to sweep from 0 to 5 in steps of 0.001. So, and then I just put plot on the inside of the loop, so the loop is just right here. And every time it loops around, it plots another Bessel function. And then I put a title and labels on it and put a legend label. So that's just replicates all the Bessel functions we just saw from the picture that's in the book. And then what I did is I took a function, I guess I created my own line function in here. So I decided to use the stem function and just have it plot the spectrum. So here I'm having it plot through all the terms, all the harmonics running from minus 100 up to 100. So I put the plus 1 in here to make sure that I go inclusively minus 100, pass through 0, and stop at plus 100. Normally Python would stop at 99, so I'm forcing it to stop at 100. And then I have it evaluate the Bessel function for a fixed index, and well, index is over a range and beta is fixed at 25, so a large value of beta. So I get all of these spectral lines over this range of IDX for some value of beta. So this is the way I left the notebook from a while back, so I'm just going to put in a small value of beta, say 0.5. And so we can see that we have a strong carrier component, and then we have a few sideband pairs. I could zoom in on those pairs, but this is for beta equals 0.5. If I say take it up to 5, we'll see that it's starting to grow bigger and bigger. And I'm also, I thought I was plotting the angle here. Yeah, I'm plotting the angle, but there it is. Okay. So now we have more sidebands. And let's just go to the value that FM broadcasting uses. It uses a deviation constant of around 75. So it has a peak deviation that goes 75 kilohertz below and 75 kilohertz above the carrier frequency. But that spreads the signal out slightly wider than that. So a single sinusoidal tone would create a spectrum that looks something like this if its deviation constant was 75. I don't know what your reaction to that is, but there's a lot of spectral lines and the spectrum is quite wide at this point. So this would be as if we were putting in 1 kilohertz for our message tone, and then it's spreading out to harmonics that exceed 75 kilohertz in either direction about the carrier. So the 0 that you see right in here is actually the carrier. So it's normalized to 0 at the carrier frequency. And the phase is not quite so exciting, but it flips sign is what it's about all it can do. The phase can either be 0 plus 1 or minus 1. And if you take, well, plus pi or minus pi. So plus and minus pi are treated in this plot to be the same thing. They're treated as pi, and then 0 degrees is 0 degrees. Does anybody have any questions? I'm looking at Slack to see if anybody messages in. Okay, I'm going to keep going. I'm going to jump back over to the lecture notes now. And if you would have been in the lab to do this experiment, number 5, you would have started by treating a signal generator as a voltage-controlled oscillator. Many years ago, the electronics class used to build a voltage-controlled oscillator in one of the lab experiments. I don't think they do that anymore. I don't know for a fact though, but they did build voltage-controlled oscillators. So a voltage-controlled oscillator is something in the analog domain that exists as a building block for an FM modulator, for a phase-locked loop, things of that sort. And I do have phase-locked loops sitting on my desk and are sitting in the lab. I mean, VCOs that are on printed circuit boards that are used in a phase-locked loop. So a simple FM modulator is to think of a voltage-controlled oscillator that has an input port and it has an output port. So the input port is where you can apply frequency modulation, M of T, and the VCO is spec'd to have a particular sensitivity of FD hertz per volt, or if it's a RF VCO, it would usually be in terms of megahertz per volt. So we can deviate the carrier about its quiescent frequency, FC, by so many megahertz per volt of input voltage. So positive voltage would swing it high, negative voltage would swing it low in frequency. So the question I have here is a homework problem, could be a quiz problem, is find A such that the spectrum of the VCO output X sub C of T contains no carrier component. So you would be inclined to say, well, if I went back over here to my cheat sheet, if it's no carrier component, you'd be inclined to say that means J0 of beta goes to 0. And you'd say, I don't know what the answer is because it happens many times. The very first time that it goes through 0 is when beta is 2.4048. And that's what I'm looking for in this particular problem. But what we're looking for then is, when does that happen? Well, beta is equal to AM times, let's see, I've got this wrong. AM times FD over FM. So in order to solve that, we have to find out what the amplitude is. So we're solving the equation. The very first time it goes through 0 is when beta is 2.4048. So we solve for A, and A is 2.4048 times FM over FD. And to complete this problem, you'd actually need to know what the tone frequency is and then what the deviation constant is for the oscillator. In this case, I applied some values here. I said suppose FM is 1 kilohertz and suppose the deviation constant of the VCO is 2.5 megahertz per volt. Then the amplitude A is 9.6192 times 10 to the minus fourth. So you're probably saying, wow, just a little bit of applied sinusoid to this high sensitivity VCO, and I've already deviated the carrier enough so that there's no spectral line at the carrier. And you're correct, that's what's going on here, because it is such a sensitive VCO, 2.5 megahertz per volt. So you can work this problem kind of like an Ohm's law equation, where you can say if you want a particular value of beta, what do you need for the other two variables, and so on and so forth. So this shows up in problems frequently for a single sinusoid. Next question is, how is the power, what is the power in an angle modulated signal? And this is deceptively simple. We just want to get the average power, and if we go ahead and use our angle bracket notation, we're talking about what's going on right here. And if you go ahead and use the trig identity to find out what cosine squared is, you get 1/2 AC squared. That's the first term, and then the second term. And the second term actually goes to 0, though, in this case. The assumption is, and it's not always true, actually in the lab experiment you got a chance to play around with this a little bit, but the assumption that's generally true in an application is, if we were looking at the carrier here to be FC and then said there's a minus carrier at minus FC, that the spectral lines are such that if you look at the 2 omega c in here, none of the spectral lines, when shifted up to 2 FC, could possibly cross through 0 and end up contributing to a non-zero average value. So in general, it's safe to say that that is equal to 0. 2 times the spectral line components that get shifted up to 2 times the carrier do not lap down into 0. There's no practical FM signal that you really want to modulate that high. But in the lab and in the experiment that is not being able, that we can't do this year, there is some playing around with that because of what the generators can do in the lab. So it's very, very easy to remember what the power is in the angle modulated carrier. It's just simply 1/2 times the amplitude squared. And the envelope, like I said before, is constant. It does not change over time. And we know that to be the case because if you look at our angle modulated signal, there's no deviation out in front. There's just AC times cosine omega c t plus phi of t. So the envelope of the angle modulated signal is a constant. So now we're going to move on. We know what the spectrum looks like for a sinusoidal angle modulation. Now we want to discuss what the bandwidth occupied is and some approximations for what's called the fractional bandwidth. I mean, right now we know from these pictures, let's just go back up here to this one. What we're seeking is, get this pen set up right. We're seeking some measure of the bandwidth. And because we know the Bessel functions for beta greater than 0 are non-zero, we know that the spectrum actually expands over a very, very wide bandwidth that approaches infinity, but they're very tiny when you get to the edges. So we're going to look for a definition that is going to give us a containment bandwidth of around, if we go back over here to our table, these single and double underlines refer to the containment bandwidth. And down here in this development right here, we're either going to be looking for 0.7, which is single, or 0.98, which is double underlines. Most of the time we're going to use the 98% bandwidth because that has a simpler relationship that we see here on this page. But that's what those single and double underlines mean in the table. How many sidebands do you have to count in order to get 98%? So that's the one we'll use most often, the 98% bandwidth of the angle modulated signal. So that gets developed here by doing an approximation, well, by observing that there's an infinite number of sidebands, but as n goes to infinity, the height of a particular Bessel function, or its amplitude, does approach 0, because we have an asymptotic formula that says it's beta to the nth over 2 to the n times n factorial. So what do you remember from calculus? What can win the race? Raising a number to power or finding the factorial? Factorials grow faster, right? So having this in the denominator drives things down towards 0, no matter what beta is. So the power ratio we're looking for here is, to relate to bandwidth, is to get a fraction of the total power, the carrier power plus the sidebands. So we sum up the fractional power, which is summing the series of the Bessel function squared from n is equal to minus k to plus k, and then we get to divide by the total power, which we can never mess up like we could very easily in amplitude modulation. Remember, there you had to get the power in the carrier plus the power in the sidebands, but the total power of an FM signal is always, or angle modulated signal, is always 1/2 the amplitude squared. So when you normalize that out, the fractional power is J0 squared, and then 2 times, because of the even symmetry, 2 times the sum of the powers in the sidebands. So our fractional bandwidth is some measure 2 times k times FM hertz. So we're counting sidebands above and below the carrier, k of them, and then we multiply by 2, and that gives us our occupied bandwidth. And like I said, it turns out that for the case of 98%, insisting that the contained power be greater than or equal to 0.98, that is the integer part, so that's what this stands for, IP. Integer part of the quantity 1 plus beta. So I wasn't planning on having a quiz on Thursday, although I can do one. I'm going to have a quiz at some time though, but maybe I'll give you a mock quiz on Thursday where we can go through an example problem where we use this formula. Does that sound reasonable? Because this is the type of thing you have to be able to do on the exam, and when you take the exam you get to have, this cheat sheet available for doing that type of a problem. So I think that would be a good practice problem to do. There is a problem kind of like that assigned for set number 8, but you don't have that due until next week. But speaking of quizzes though, it's been suggested to me that a way of doing a quiz is to have everybody turn on their camera and let me watch what you're doing while you're taking a quiz. I'm throwing that out there right now because I'd like to know if everybody has a camera that they can have on them while they're doing something. You don't have to answer that verbally, but I'd certainly like to hear that in Slack for you to respond to me. And if you want to do it on the private channel, that's fine too, or the direct channel, I don't care. But I do want to know does everybody have access to a camera so that when they're taking an exam or a quiz, I can be using that as some control over what you're up to. Okay, that's good. Where did I get this idea from? Well, all of us last week during spring break, Dr. Kelker asked us to give him an update on how our teaching was going, and I didn't have to give an exam the week before last or a quiz, but Dr. Song told us, all of us faculty, that she used that and she was happy with the way it worked. And some of you probably have her for Fields and Waves right now, so I'm guessing that's the class that she used it in. Okay, thank you for responding. It's nice to know. We might use, rather than daily, we might use Zoom, because I think it has a nicer array of images that we can come up with. So I might practice with Zoom on Thursday just to see how that works as opposed to daily. If you're wondering why I don't use Zoom, because you think Zoom is great, Zoom is not free, and if you use the free version of Zoom, you can only talk for 45 minutes before the video shuts off. So that's not acceptable for a long session. It's only acceptable for the length of a quiz. And right now, UCCS doesn't have a license for Zoom. Boulder does, but UCCS doesn't. Instead, we have video conferencing through Microsoft Teams, but we got some reports from other faculty that Teams wasn't working necessarily the greatest either. At least the news that I had when other faculty gave their reports is that they had problems with video dropout. And some people tried to record their lectures using Teams, and that didn't work very well at all because it took a very long time for the video to get produced. So I'm not going that route. I'm glad we had that interchange last week. I'm just going to stick with Slack for the time being. And the fact that I'm making my video right now means that I have total control over it. I don't have to worry about the cloud processing it or being any distortions in the cloud capturing it. So that way I've got the video available for asynchronous learning after the lecture's over. So looking at what we have here for sinusoidal FM, we have this formula. So we will use this from now on. I don't really care about the single underline. I only care about the double underline on the table. But 2 times beta plus 1 times FM is going to be our formula for getting the bandwidth of a sinusoidal modulation. But then we want to move to a general result where we have a general signal, not just a single sinusoid. Then we can move to a more general result known as Carson's rule. And we can get that formula by creating this definition called deviation ratio. So we define the deviation ratio, D, as the peak frequency deviation divided by the bandwidth of the signal. So this is a definition that works for angle modulation, frequency modulation. D takes the place of beta. Except now we just have to have the bandwidth of our message and the peak deviation that the message is pushing the carrier to while the modulation's taking place. And that formula ends up just being expanded out as FD, the deviation constant for the modulator, times the maximum value of our message, and then divided by W. So if you write that out as Carson's rule, then you're replacing beta from this equation becomes D down in here, and that gives us the bandwidth of a general modulation scenario where D is the peak, is the deviation ratio. Then another rule that I think is very handy, I don't have it blue boxed here, but this shows up in a homework problem that I'll give you later. I think it's on set number 9, but I'll probably have this problem up here. We can also work with the peak frequency deviation, delta F, and come up with an equation that says beta, or bandwidth B, is 2 times the quantity W plus delta F. And all we have to do is understand that delta F is just this portion right in here. In a lot of circumstances, this makes a lot more sense because you're looking at what your message or information is doing. What's the maximum push of the frequency or deviation of the frequency over time? And that's what delta F is, the maximum frequency deviation. Now, deviation is double-sided though, so delta F is the swing in one direction, and then presumably if the message is symmetrical, it swings it back in the other direction by the same amount. So just keep that in mind, that you can also write that as 2W plus delta F, and you can get that by recognizing that I'm going to go down here and write it out. How could we prove that? Well, what you can do is you can take bring delta F, let's see what I want to bring out of here. No, bring W out of here. If I bring W out of there, then I get 1 plus delta F over W, and delta F over W is just D from the definition up above. So those two are interchangeable. And what I like about them is that the first one follows directly from the development from the Bessel functions for the special case of the sinusoidal modulation. But the second definition is nice because it says that, okay, the bandwidth is composed of 2 parts, 2W, which is like double sideband is what I wanted to say. Right? If you double sideband modulate a carrier, the bandwidth on the carrier is going to be 2 times W. Then you have this 2 delta F, so the bandwidth expands further by whatever delta F happens to be, which is the peak frequency deviation. Okay, talk about the Python project. Yes, I can do that. I guess I ought to switch to that. But, okay, that's all I want to say on that for right now. So I have 2 directions I can take in the remaining time, which is about 5 minutes. Number 1, I could go talk about the project. Number 2, I could talk about the homework. I've had a request from one student to give more time on the project, and I thought that's a bigger task than working on the 2 problems for the homework. And I realized when I made this assignment I was doubling up. I was making homework due on the same day the project would be due. So which would you rather have me talk about, and which would you rather have me give you more time on, the homework or the project? Okay, I like that idea. And Jared, I didn't know you were signed in right now, but I don't know, is anybody teaming right now? Those of you that are undergraduates, and there's 4 of you, you can team if you want to, and you can use Slack here to do your teaming. Okay, well, we got John who wants more time on the homework. Let's take one thing at a time. Is anybody teaming on the project? I was sort of tacitly assuming that maybe Colton and Will were going to team, and then that would leave Chris and Jared to team. But I don't know if you guys can do that or not, or want to go for it. You can do video conferencing on Slack. You can message on Slack. You can share screens. You can turn in one project if you team. Is anybody thinking about that? No comment?
Can you not hear me?
I can hear you just fine.
Okay, I was talking earlier and it wasn't working.
Okay, I hear you great, actually.
Okay.
I like to hear people because I feel like I'm talking to myself otherwise, but Slack is a second best, so. So
Well optimized that.
Chris would work with you, maybe work with you, Jared, but that's between you two, and I'll let you guys discuss that on a direct channel or direct messaging later.
I'll reach out to him, see where he's at.
Yeah, I don't know
But
about
it's a
Will.
hard Friday.
Pardon me?
It's a hard Friday.
No, it's
Friday.
not. It's not. I would like to give you until Monday or maybe even Wednesday for the project because I'd like to have one more set of discussion on it. But let's just hold on Tuesday for right now because we're on Tuesday right now. We're not out of time yet. I think the homework though is very doable for Friday just to get that done. One student turned it in last week already, so it's on a different topic. Pardon me?
Which homework was it? I'm losing track of things.
Number 7.
The one you just posted?
No, number 7 was posted at the end of around the 20th is when I posted number 7.
Okay.
I'm going to open it up here though. And I will get myself pinned folders 5625. Set 7 hints. This is on bandpass sampling. Well, one's on bandpass sampling, the other is a drill problem related to the bandwidth of a PCM signal composed of different types of digital modulation. In this case, it says digital multiplexing with PCM with 16 bits per sample for each of the signals, and I've modified the problem to just say what's the bandwidth. And that's a very simple problem. You're just adding up the bit rates, knowing that you've got 16 bits per sample, but you do have to read the problem to know what the sampling rate is that's needed in the problem, and that's based on the bandwidth of the message signal for that problem. Problem number 6 though is more challenging for sure, and I have guidelines on that in the notebook for chapter 3, and I have hints that I've posted up there too. You want to use tools that are in the notebook though. And those tools are in chapter 3. And if I get this to switch over for me, drop down to the bottom. It seems like when I get near the end of the lecture, I've gotten a lot of video recorded and I'm getting a computer that's just about ready to melt down. It's not responding very well. It's very sluggish at this point. Shape of things to come for tomorrow morning when I have to make this last for 3 hours. Bandpass sampling theory. So this is what you want to do to work that second homework problem. And then of course you want to read the hints that I have over here. Oh, here's some hints for the multiplexing problem, besides what I wrote down in here. But for problem number 6, I wrote down a lot of discussion and things to try to make this work. It's something that requires a little bit of finagling and finessing. What you're trying to do is you're trying to find an undersampling frequency that will allow you to sample the bandpass signal but not incur any aliasing. And the way you get to visualize whether or not you have an aliasing problem is to use this function right here to have it draw pictures for you. And I can see that this notebook has not been initialized yet since my systems have rebooted. All my Windows systems rebooted the last couple of days. So once that function is run, then you can run an example here, and you can get a spectrum plot with undersampling. Here I'm not really undersampling at all, but what you can do is you can choose to undersample. So right here, what I'm saying with this function, the number of translates that you want to display, but then you get to put in the range that you want to plot over, the sampling rate, and then this is how your bandpass signal is defined. It runs from 2 to 3. In the case of the homework problem, the problem is set up as if you were building a DSP sampling, undersampling type radio where you've got an IF near 10.7 megahertz. The bandwidth of your message is at 200 kilohertz. So you wanted to know how much undersampling you can apply in that case. So you've got a spectral scenario like this. What you'd like to be able to do is undersample. In other words, you don't want to sample at twice the highest frequency, which would be, roughly 2 times 10.7 megahertz. You want to be able to sample at something less than that according to the bandpass sampling theorem. And what you need to be able to do is satisfy these two equations in order to make that happen. And then you can verify that over here in Python. So we'll talk more about this next time, but I'll just give you an idea of what you could do right here. Suppose here, rather than sampling at fs equals 10, suppose I'd try to sample exactly at twice the bandwidth of my signal, and the bandwidth of my signal is from 4 to 5 hertz. So if I sample at 2 times that, 2 times 1, and keep my sampling, do 2 times 1, takes a while to draw all the translates up, so that's what it's doing right now. This is working because we have these two triangles aren't crossing through each other. What you'd want to do at this point is zoom that interval, so you'd want to do this again, which is kind of painful, but you'd go plot from, let's see, about -1 to 1. So I'd do an xlim. Oops. What's going on here? What you end up proving in this problem is when you zoom in, what you're trying to do is you're trying to see, is there any collision going on in here? So I probably should have gone up a little bit higher. like 1.2 or so. It's so slow. It's acting like I can't slow my brain down enough for my way my computer's behaving right now. Okay, so I would say that it's working for this particular example, it's working. And what you have to do in the homework problem, though, is a little bit different. It's a little bit more challenging, and I walk through that pretty readily in here, and I talk about how you can verify this with guard bands. And I don't know, I'd like to have you read through it before I try to say anything more, but we'll kick off lecture on Thursday with this discussion. If you're anxious to have me give you some more hints, you can fire at me over Slack between now and Thursday as well. We are out of time. I guess, Colton, since you wanted to talk about the project, what is hanging you on the project right now? Because I'm going to go over to what I posted last week, or before last week, actually. I posted, things are getting definitely slower. I'm going to go up here under problem projects. This was intended to help focus you on one of the more important, the important focus of the problem of the project is what are the filter design needs, and then how do you code to meet those design needs. So I lay it out here with these bullets, but pictorially I created this nice little hand-drawn picture right here. Do I need to zoom that to help you see it better? Or is it okay?
It's fine.
Okay. So I go through the entire block diagram down below here, and then I point out where filters are needed. So single sideband modulator is Weaver, and in the Weaver you have the need for a low pass filter that goes from 0 to 2 kilohertz, and the folding frequency in that case is 4K because this is 8 kilohertz. And then in a second filter you need is another low pass filter that cuts off at 4 kilohertz, but this filter design, the sampling rate is at 96 kilosamples. So those are the first two filters. And then the second two filters that you need are in the coherent demodulator. You need a low pass filter for a decimator that downsamples from 96K back to 8K, and that filter can serve both as the decimation low pass filter before you downsample by 12, and also as the low pass filter in your coherent demodulator. So that rolls up into 1. So that's filter 3. And then filter 4 is you need a bandpass filter to protect your coherent demodulator from seeing one of the adjacent channels. And that filter is centered halfway between the carrier frequency that you want to receive and 4K above that. So this green filter would be setting, say, over message M1, or if you're going to be selecting to receive message M2, it has to sit here, or if you want to receive message M0, it has to sit over here. So this is actually a tunable filter. In code, when you select which channel you want to receive, you design this on the fly, and then this filter sits. So suppose you want to receive M1. This filter is vital because if you don't put this filter in here, your coherent DMOD puts the carrier right here, and you want to get this signal back, but this other adjacent signal is sitting there acting like a lower sideband signal, but it's actually a completely different message. And if you don't design the filter properly, you hear the message M1 plus you hear M0 spectrally inverted, which is gibberish sounding. I'd say go ahead and mess up just so you can hear it, because you won't be able to, it'll be unintelligible, but this signal will demodulate even though it's not what you want to get because it's from another channel. You will hear it when you're trying to recover M1. And depending upon how much effort you put in your filter design, you'll hear it a little bit anyway. And I don't want you to put an extreme effort into the filter design. I want the filter designs to be as minimal as possible. The objective of this is not to over-design your filters, because in a real system you just can't do that. You have to do what you have to do. And I walked through some examples in here about how you might do that, how you might design the filters. In particular, one of the things I spend a lot of time on is, suppose this is your interpolation low-pass filter, which has a sampling rate of 96K and it has a cutoff at 4K. So I design using the filter design functions in my toolbox, IIRD, and then you're going to design an IIR low-pass. I have you set the cutoff frequency at just below 4K, and then you set the stop band attenuation frequency, or the stop band starts at 4K plus DF4K. So in this particular design here, I'm setting, actually it looks like I have a typo in here. This is supposed to say 4K. This is a typo. I'm going to have to go fix that, repost that, but this should say 4K. This is for 96K, I believe. I'll check this out, and you'll probably see me reposting this later tonight. This is supposed to be a 4K filter. It looks like I cut and pasted something wrong. This filter up here is the Weaver filter. This one cuts off at 2K. So this is a 2K, but I just pasted something in here incorrectly, because my filter obviously came out okay in this example, but I don't know if that helps you, Colton, but
my phone's about to die. I'll DM you in a bit.
okay. I'm going to be out walking my dog with my son, so I'll be out for about an hour going around the block here. But Slack is always slacking me anymore, so and more people have joined Slack because I've had 2 design teams join, so I'm definitely staying busy, which is why I'm not grading any papers yet. It's just a lot. Never a dull moment, though. I don't know. Honestly, have any of you been bored over spring break?
Nope, just very stressed for no specific reason.
Well, if you watch the TV news, you get stressed, right? It's not the news.
I don't need it.
Okay.
I've been resetting up my home network. I've had to build 3 offices. Like, it's terrible.
For your own self or for somebody you're working for?
Oh yeah, for my office. My wife is working from home. I had to move my mom's office so she could be isolated from us. I got my kids here.
So it's kind of crowded then.
Yeah, no, I've got 2 classrooms and 3 offices. So, yeah, no, it's
Not enough hours in the day.
Yeah, okay, I can.
No, I'm losing it.
Well, try to take some breaks. That's why I take breaks. I don't like talking to people. I run into people, but I don't get very close to them when I'm out walking.
I don't have much time.
Well, do what you need to do, though. Don't watch too much TV news, though, is what I'd recommend, because it's kind of depressing. A lot of it is.
Whatever you do, don't look on the Johns Hopkins website.
Oh, okay. Well, our dean, I'll put up messages that our dean sends us, but yesterday the dean sent us a message saying that a prediction from somebody within the CU system is that Colorado will not reach its peak until the end of April. Like May 1st is when the peak will occur for Colorado. So
That's what happens when you self-isolate. It extends the pandemic.
you want to extend it by being self-isolated?
No, that's the consequence.
Yeah. Mean a slower growth rate to the peak because we're self-isolating?
Yeah, so it leaks for longer.
But we're trying to keep the hospitals from getting overloaded at this point.
Correct.
So, yeah, there's pros and cons to this. We're all engineers, so our brains are whirling away on math models for this thing, right? Or maybe you're not thinking of a model because they talk about the model a lot on TV.
definitely think about the model more than I should.
Yeah. Well, I'm going to sign off for now so I can get the video processing here too. I think today's session went pretty well. I think actually we've got everybody today, is what I'm thinking. If I was to go switch and look at my daily tab. And yep, we don't quite have everybody, but maybe somebody signed off. I guess Colton signed off, but so I'm going to finish my
everybody's
video
signing
up.
off.
What's that?
It's like everybody's signing off.
Yeah, which is fine. I'll be talking to you guys. It's just a different life right now is all I can say. Most of my graduate students, like I said, are bored and they're just working hyperdrive because they have to stay busy. And so that means I'm busy answering questions all the time, but we're making progress. So see you guys next time around, and I'll be chatting with you too. Bye for now.